often in real problems, it turns out that two different variables are changing with one another in the problem. As an example, suppose I'm standing in a position and I'm watching a train go by. And you think about the angle, my eye angle, sort of looking at the train. As the train goes by, when it's far in the distance, I'm just kind of looking like this. And then as it gets closer, I start to move a little bit, and then it goes by like this. That is, I'm changing the rate of turn of my head to see the train. If the train is a long distance away, you don't really notice very much of a change. But if the tracks are right here, then I'm looking at the train and here it comes, and then all of a sudden, whoom, it goes by. And so I'm moving very quickly. Now, we have a wonderful ability here in calculus to freeze time. This derivative idea is a change at a moment, rate of change at a point, rate of change at a point in time. And so we're going to sort of freeze time with a couple of problems here in just a minute. But I just want to tell you that now the variables that are changing, the angle of my head is one variable that's changing in this problem. But maybe the speed of the train has a lot to do with it too. It does have a lot to do with it. The speed of the train is a factor. The distance that the track is from me, those are all factors in the problem. And if we can somehow relate those ideas with equations, and use the idea of derivative, then we can find out all sorts of stuff. Take this problem as an example. A rock is dropped into a pond, causing circular ripples. If the radius of a ripple is increasing at 1 foot per second. Now let's stop right there and let's talk about that. So a rock is dropped into a pond, a splash is made, and here goes a ripple. And it's a circular ripple that's coming out. And it's going out from the center at a certain rate. All right, that's what we're talking about here. And that rate can be measured by the change in the radius. So that the radius of the circle is moving out. Now let's continue. So the radius of a ripple is increasing at 1 foot per second. At what rate is the area of the circle increasing when the radius reaches 4 feet? So as that circle, you see, is growing larger and larger, the radius is getting wider and wider, the area is getting bigger and bigger, the area of the circle is getting bigger and bigger. Now, can we freeze time when that radius gets to be exactly 4 feet? Sure we can. And the freezing of time and thinking of a rate at a moment in time is what derivative is all about. Now just understand too that this transition or this calculation of derivative, the notation of it, what does the notation mean? Well, come over here and let's take a few examples so we can get a handle on this. That if a train is going 30 miles per hour and x is some distance traveled, then the derivative of x, dx over dt, the derivative of distance in terms of time, is a rate. It is the 30 miles per hour that we're talking about up here. Change in distance per unit of time. Change in distance, change in time. If a fire hose is kicking out 25 cubic feet of water per minute, 25 cubic feet per minute, you see that's sounds like kind of a rate. But if we're talking about the volume of water that is involved here, and firemen might want to know about the volume of water that they're putting onto a roof, and how much it weighs and all sorts of stuff like that, so they'll know when the roof is going to collapse. But at any rate, the notion is if the fire hose is putting out 25 cubic feet per minute, then dV over dt, the derivative of volume according to time, we're freezing. We're talking about the rate of the volume at a moment in time is 25 cubic feet per minute. You see this direct correspondence here, and here is our interpretation in calculus for that idea. Now this one is a little more elusive. We have to reach out for this one a little bit. A car has a certain RPM. the engine is running at a certain number of revolutions per minute. The shaft is turning over at this rate, revolutions per minute. Now, if theta is the angle of revolution, you know, if it's just a change in angle. When we're going around and around, it's kind of like my head turning. That's the change in theta, you see, and some kind of angle when we're just moving around like this. So theta is an angle of revolution, then d theta over dt means the derivative of theta in terms of time, or it's a frozen moment. It's a rate of change in theta at a point in time. And that's just 2,500 RPMs. Now, if we're talking about this theta angle business, now angular change is according to a theta within a circle. And you know that a complete revolution of a circle is an angle of 2 pi radians. So if we put that idea, this RPM, revolutions, well, each revolution is 2 pi. So this would be 5,000 pi radians per minute, you see, is this angular velocity that we're talking about here. Well, okay, so our notion of derivative allows us to freeze a moment in time. And all we need to do in problems such as this one is have a relationship between the variables. And there's a nice built-in relationship between the variables here. We're talking about radius changing, area changing. We have a formula that relates area and radius. It is the area of a circle is pi times radius squared. Now notice what we're doing here is this circle is changing like this. This circle is going out, and at the moment in time when that radius reaches 4 feet, we want to know where, at what rate is the volume, is the area of the circle changing. Okay, so area is pi r squared. Now, implicitly differentiate on both sides according to time. According to time. This rate that we're talking about is a rate, a volume at a moment in time. So we are differentiating with respect to t. And so here we have a dA dt, the change in area at a moment in time, or with respect to time. And on the right, we're doing the same thing. We are differentiating with respect to t. We're differentiating the radius with respect to t, or r with respect to t. So implicitly it is, let's see, 2r, pi times 2r, and the dr dt with respect to time. You see, radius with respect to time. Now, what do these things mean? Well, this is what we're looking for. If we're thinking about what is the change in area at that moment in time, that is what dA dt is. That's the symbol for it. And dr dt, well, we were talking about the rate at which the radius is changing. It's changing at a constant rate of 1 foot per second, we were told. So this dr dt is 1 foot per second. And we're talking about at the moment that we're making this calculation, the radius is 4 feet. So this is 2 times 4, or pi times 2 times 4, or 2 pi times 4. Now, I'm putting the units in here so that we'll be able to look at the unit in our answer. A lot of times, if it's at all confusing, all you have to do is put the units into the problem, and the unit at the end of the problem drops out very nicely. So here we have a radius of 4 feet. We have 1 foot per second, and then we have feet times foot, or feet times feet, feet squared, square feet. So square feet per second is the unit down here. So it's 8 pi feet per second is the rate of the change of the area of the circle at that moment in time when the radius gets to be 4 feet. Here's another example. A balloon is inflating at 4.5 cubic inches per minute. So a balloon is being blown up, and 4.5 cubic inches of air per minute is being put into the balloon, and the balloon is expanding. Find the rate of change of the radius of the balloon when the radius is 2 inches. So at the point where the balloon grows to a radius of 2 inches, at what rate we're saying, let's see, find the rate of change of the radius when that radius reaches 2 inches. All right. We need a relationship between volume, or how do we think about the volume changing in this kind of figure. It's a sphere, you see, or it's roughly a sphere. Actually, it's not exactly spherical, but it's close enough for us to make the calculation. All right, the volume of a sphere is 4/3 pi r cubed, and oh, by the way, this 4/3 pi r cubed, this volume formula comes from Archimedes, and if you ever get a chance, you should read about the derivation of this formula and what Archimedes did to derive this, to find this formula. Very interesting situation. Archimedes himself is a very interesting character historically. One of the 3 great mathematicians in all of history. Anyway, the derivative, the implicit derivative is, let's see, this would be a dv over dt. This would be 4/3 pi 3r squared. Now the derivative is the derivative of radius with respect to time, so it's a dr dt. Now what are we looking for and what do we know at this point in the problem? Well, when we're asked to find the rate of change of the radius, you see, at a point in time, that's the dr dt. So we're looking for the dr dt here. We're looking for that. Now, so we need to solve for that in our problem. Now, what is this then? What is dv dt? Well, that's the change in volume in terms of time. And that change in volume is nothing but this. We're just adding a constant 4.5 cubic inches per minute. So that's really what this part is. Well, let's clean up a little bit. We have, let's see, the 3's go out here, and we've got 4 pi r squared times dr dt. Now I've repeated that up here. So 4 pi r squared dr dt on the right. And we're just plugging in for this volume rate at a moment in time. That's the 4.5. And then dividing on both sides, let's see, by this coefficient, this would be 2 squared. Oh, incidentally, I popped in the radius of 2 because it said we're calculating this at the moment that radius reaches 2. When that balloon is expanding and the radius reaches 2, what is the rate of change of the volume? That's what we're asking. Okay, so the 2 is popped in here for radius. 2 squared is 4. 4 times 4 is 16. This is 16 pi. Dividing on both sides by 16 pi, we get this. And we find that dr dt is approximately 9/100 inches per minute at that moment in time. An airplane is flying at an altitude of 6 miles on a path that will take it directly over a radar tracking station. If the distance from the radar station is decreasing at a rate of 400 miles per hour when the distance is 10 miles, what is the speed of the airplane? The confusing part here is the notion of the 400 miles per hour when the distance is 10 miles. You see the airplane is not coming exactly straight toward the tracking station, but the distance between the radar unit and the airplane is decreasing at 400 miles per hour at a certain moment in time. And that moment in time is when the distance between them is 10 miles. Let's outline our information. We know that the altitude of the airplane is 6 miles. The distance between the radar unit and the airplane is decreasing at 400 miles per hour when that distance between them is 10 miles. And we're looking for the speed of the airplane. Here's a diagram. Here comes the airplane, and at this one moment in time, the airplane is 6 miles high, and it is approaching the radar unit at 400 miles per hour. So that distance is decreasing at 400 miles per hour at the moment when that distance is exactly 10 miles. This is the notion in terms of derivative of some derivative in terms of time, or some d dt. Now we haven't attached a label to that variable distance, so we don't have an additional letter in the numerator, but that's what we're going to come back to in just a little bit in our problem. What we're looking for here is the speed of the airplane. Well, we have a right triangle situation. Let's put some labels on this. Let's call the distance between the airplane and the radar unit S, and to complete the triangulation we'll call this value x. Now it's the change in x that we're really looking for here, because it's the change in x that's the speed of the airplane. And if we flip-flop the right triangulation, we can see it even better. So we're looking for that change in x. Now the relationship, because we have a right triangle, is x squared plus 6 squared is s squared. And we can go through and differentiate implicitly through the problem. So for the first part, it would be, to differentiate x squared, it's 2x, and it's a dx dt. And for the constant just goes out, and for s squared, it's 2s, and it's a ds dt. Now, the change in x with respect to time is really what we're looking for here. That's the speed of the airplane. So we want to solve for the dx dt in our problem before we go any further. So with our equation, we'll divide on both sides by 2x, and we have some nice expected cancellations on both sides, so dx dt is equal to this. Now we have some information about the expression on the right side. S is exactly 10. That distance from the airplane to the radar unit you see was s, and that distance is 10 at a moment in time. The ds dt is the change in that distance with respect to time. And that was the 400 miles per hour. Now, we could list this here as 400 miles per hour. I could list it as negative 400 miles per hour because it's a decreasing distance, but it really doesn't make too much difference in this problem. Now, the x is an interesting matter. You know, x is this part at the top, and we can actually make a calculation for x at a moment in time when s is 10. So we can let s be 10 and solve for x. And we can do that by taking this relationship at the top and just make the replacement for s. When s is 10, then we would have 10 squared on the right. So we'll have 100 minus 36, so x squared is 64, and x then is 8. And we just pop that x of 8 into our equation, and we'll solve for the dx dt. dx dt is 500, and that's 500 miles per hour. So the speed of the airplane when s is 10 miles is 500 miles per hour.